Hello, everyone. Good morning, good afternoon, good evening. This is the first lecture of STAT 248, Couplings in Monte Carlo. And so we will start with a quick overview of what this course is about. I'll introduce myself and I'll introduce Rohit Chaudhuri, the teaching fellow. And then we'll dive right into the material. So this course has been taught remotely last spring at the University of Torino in Italy, as part of a sabbatical that I was taking from Harvard, but this is the first time it is taught at Harvard. So, you know, a lot of it is then a bit experimental. And in a nutshell, it's a course about probability and computation focused on the class of Monte Carlo algorithms that are used a lot in statistics, but also in other fields to approximate probability distributions or integrals, volumes, and so on. And so in this course, you will learn about algorithms and probability in general, and in particular about different notions of distances between probability, which will be the opportunity to learn about some recent advances, such as optimal transport, for example. So some of the material that we're going to talk about is very old. I mean, some of the couplings date back to the 1930s. But some of the material will also be at the research forefront. So we'll see some material such as some algorithms used in statistics, machine learning, and so on that are much more recent. Some of it is from the past few years. Okay, so let's have a look at the Canvas website and I'll introduce the staff. So now we're on the Canvas website. For the course, and all of the information that you need should be on the Canvas website. Okay, it's going to be progressively added throughout the semester. And so in particular, you'll find all the files you need to follow the course, but also the announcements and the pieces of news that will inform you about all the times, the times for the lectures and the office hours and so on. So for example, at the moment, there's a little calendar of week 1 where you can see all the days of the next week with some information that will get updated about what's going on with the course each day. So the goal is that, of course, this should be easier for you if it's all in one place. And so hopefully everything will be available on this page. So to introduce the staff, so I'll start with Rohit Chaudhuri. There's a link to his website here. This is Rohit. Rohit is a third-year graduate student in the Department of Statistics. He's a specialist in probability, in random matrices, and Markov chains. He has a lot of teaching experience. He's taught Stat 211, which is statistical inference 1, and Stat 213 last year, which is statistical inference 2. And so it will be super useful to you and also to me throughout this semester. So I'm sure you enjoy interacting with him. Myself, I'm a faculty in the stats department since 2015. Here's my website. On my website, you'll find more about my research if you're interested. You'll see that it's it's very much related to the topics of the course. And so a little biography. I was educated in France, and I moved for postdoctoral positions in Singapore in 2013, and then in the University of Oxford in 2014-15, and I arrived in Harvard in 2015. I've taught courses on time series analysis and statistical inference before. And as I said, this is the first time this course is given at Harvard. Now on my website, you will find a link on this tab called Couplings in Monte Carlo with all the material that was related to the version of the course given in Torino last year. And so I will keep this unchanged. But as far as you're concerned for this course, you shouldn't really care about what's on there. You should care only about what's on the Canvas website. The material that is in there on my website, it's outdated. But you'll find a link to YouTube videos and lecture notes and some pieces of code. So of course, you're absolutely welcome to have a look if you want to especially see what's coming next, you can have a look at the videos and the lecture notes. But that being said, I'm going to work on new versions of everything. So you might as well just wait on seeing what's going to be uploaded on the Canvas website. Okay, so just out of curiosity, you can have a look at this. So in terms of the organization of the course on a weekly basis, here's what we have in mind so far. So there will be one video, such as this one, available every week. Extensive lecture notes, we'll have a look in a minute at the lecture notes that are already available on the Canvas website. And then the hope is that the synchronous time that we'll have together, which will be on Monday and Wednesday, 9 a.m. in US Eastern time, will be as interactive as possible. So for that, of course, I encourage all of you to have a look at the material beforehand and to come with questions. So the idea I have at the moment is that on Monday, we'll have Q&A about the material. So you'll come with questions and we will discuss any points that you want to discuss relating to the videos or to the lecture notes or the exercises and so on. And on Wednesday, we'll have a more exercise-driven lecture. So we'll be all together. I'll propose some questions that are related to the part of the course we are talking about that week. So for instance, the first week, it will be about Monte Carlo methods. And we'll have breakout rooms and interaction between yourselves and between you and me to go through different questions that we'll try to solve together. So that's for the organization of the course. So now let's have a look at the material that is already available. First, the lecture notes, and then the exercises. So the lecture notes look like this at the moment. So this is the first chapter. There will be 4 chapters in total. We might not cover everything that is in the lecture notes, but only a subset of it. You'll find visualizations, and hopefully it will be most of the topics should be covered in the lecture notes. And of course, I welcome any feedback on the lecture notes. If there's anything unclear or typos, mistakes, please reach out, let me know. So that's the lecture notes. So again, there will be 4 in total. Now let's have a look at the exercise, and I'll briefly describe what the assessment will be for this course. So at the moment, you'll find on the Canvas website this document, which is a list of projects or exercises related to the first chapter of the lecture notes. So there will be a list also for the second chapter uploaded later on, and for the third chapter. And so at the moment, you'll see 10 different exercises. Some of them are really more like exercise that you can do a bit like a written exam if you want. And other ones, like the first 3 or 4, they're more like projects. So they're a bit open-ended, and you're free to answer the question the way you want. For example, you can write a report. You have freedom on the length of the report. You can instead do a video if you prefer, or do a piece of code and explain in a video the result of your piece of code. So there's a bit of freedom. And if you're not sure, of course, you can ask Rohit or myself during office hours or during the classes what exactly we have in mind for those exercises. So the idea of this list of exercises is that you don't have to do all of them. Instead, you'll have to do a total number of them throughout the semester that you can choose in each of the lists. Okay, there's a number of constraints that are going to be explained on the Canvas website. For example, you'll have to do a minimal number of exercises related to each of the chapters. For instance, maybe at least 2 of each chapter, and maybe the total number will be maybe 10. So that will be the way that we assess you during this course. Of course, if you're not auditing this course. And the other way of assessing your engagement in the course will be through projects. So the projects will be for the later part of the course, and they will result in either reports or videos that you will present that will be perhaps also available to the other students. All of these, the exercises and the projects, you can do in groups of maybe 2 or 3 people. You can talk to Rohit and I about this. If you want to do it in group, but you don't know with whom, please reach out and we'll help you find people to work with. Okay. Ideally, please work with people who have different skills. So for instance, it'd be nice if you interacted between graduates and undergraduate students, and we can help you doing this matching if you're interested. So this is for the exercise. Again, there will be clearer instructions on the Canvas website as we progress through the first week of the course. Okay, so we've talked about the general organization of the course. A lot of it is a bit tentative because this is the first time this course is given, and of course in the context of remote teaching. And a reason also why this is a bit tentative is that we're not yet sure how many people are going to enroll. This is going to be between maybe 10 and 30 at the moment, so it's quite a big range. And depending on that, we might adjust a little bit how the course is gonna go on a weekly basis. And so we'll keep you posted as soon as possible. Probably everything will become more solid during the first week or 2. Okay, and then without further ado, I'm going to dive into the material of the first chapter of the lecture notes. And so we're going to talk about Monte Carlo. So let's talk about Monte Carlo. So generally, Monte Carlo methods refer to methods to obtain samples or draws from probability distributions. We will denote them by pi, and since they are the objective of the methods, we will call them the target distributions. So Monte Carlo methods are algorithms, which means they have inputs and outputs. And so we'll talk about the inputs and the outputs of Monte Carlo methods. So as the input, we need some knowledge, of course, about the target distribution pi. If we want to have samples from pi, we need to know something about pi. There will be no magic, right? So for example, what we might know is a way of evaluating the probability density function of pi. This is one of the possible things we might know, or we might not know. And so we'll talk about the different inputs. In terms of output, we will want to get samples, x1 to xn, from the distribution pi. That's the overall goal of the Monte Carlo method. So what does it mean? It means that if we consider a set A, a measurable set A in the space, the probability that our sample xn will be in the set A should be driven by the probability distribution pi. So it should be the integral over A of pi dx. So this should be exactly true, or at least approximately true in a sense that we will make precise later on. For example, in the case of Markov chain Monte Carlo. So why do we care about those kind of algorithms? Well, those Monte Carlo algorithms really constitute a way of understanding probability. Once we get samples from a probability, we can visualize the marginal components of the probability, all sorts of transformations of them. We can compute those probabilities, so the probability that the samples will fall in a certain subset of the space, and so on and so forth. So really, in a sense, Monte Carlo methods are really a computational companion to probability in quite some generality. So this course could also be called, in some sense, computational probability, in the same way that people talk about computational statistics. Now let's focus a little bit on the input knowledge that will feed the algorithms for generating samples from the target distributions pi. So as we said, we could be in the capacity to evaluate the target probability density function pointwise. So we know how to evaluate the function that maps x to pi of x, if that refers to the PDF of pi. That's quite rare, actually. More often, we know how to evaluate what's called the unnormalized density. So another function pi u of x, called the unnormalized density, which is equal to pi of x up to a multiplicative constant. So pi of x is equal to pi u of x divided by z for all x, where z is the normalizing constant. And since pi of x integrates to 1, z must be equal to the integral of pi u of x dx. So in many cases, we'll be in that situation where we know how to evaluate pi u of x, and we don't know the normalizing constant. For example, in Bayesian inference, this is the standard setting. Now, in other cases, for example, in dimension 1, we might have access to, for example, the cumulative distribution function. So that's the function f of t equal to the probability that x is less than little t. So that's, of course, only defined if x is in one dimension, where x here refers to a variable that follows the distribution pi. Or we might have access to, instead of the CDF, the MGF, the moment generating function, and so on and so forth. So there are many cases, because users might have many different types of information, and that leads to many Monte Carlo methods. So the reason why there is so many Monte Carlo methods is not only because they get better and better at doing one thing, but it's because they're tackling many different situations. So importantly, don't be too much scared about the variety of methods. So now let's talk about the output of Monte Carlo methods. As we've said, they're designed to generate samples. We're denoting the samples by x1 to xn. We call them samples or draws from the target distribution pi. So in the first methods that we will see, those samples will be IID from pi, which means independent and identically distributed, all distributed according to pi. In later methods, and in most sort of state-of-the-art methods, we don't actually get IID samples, we get approximate samples. So they will be, of course, approximate, so not IID, but of course valid in some very formal sense, which we will talk about at length during this course. And so what could we mean by valid? So let's take an example. If we take a certain function of the state space, which we might call, so the function we might call h, of the state space we might call x, to the real line, we might want the average of the function evaluations on the samples to converge as n goes to infinity towards the integral of h of x pi dx. So this quantity on the right hand side can also be written as an expectation with a big E with respect to pi of the variable h of capital X. So what do we have? We have a law of large number. We have an average converging to an expectation. And so this might hold, of course, under very well-known conditions for IID samples. If we just assume that the integral of the absolute value of h of x with respect to pi is finite, we have the law of large number. But this might also hold for, more generally, other types of samples, for example, weighted samples or Markov chain samples. So for example, if the samples have weights, so unequal weights, what might replace this law of large number is the following one. So we might want that the ratio of the sum of the weights times the function evaluations divided by the sum of the weights. So this is a weighted average of the function evaluations. We might want these to converge to the same expectation on the right-hand side. So then we'll have a law of large number for weighted samples. And again, this might also work if we don't have IID x's. So for example, if the x's are all along the trajectory of a single Markov chain, for example, as will be the case with Markov chain Monte Carlo methods. And of course, we might not only care about laws of large numbers, we might care about central limit theorems, for example, from which we can obtain confidence intervals for the quantities of interest. We might care about other sorts of probability statements about the output samples. Now the course is about Monte Carlo, but also about couplings. So next, let us discuss a little bit what is meant by couplings. So couplings are simply joint distributions, so multivariate distributions, which have given marginal distributions. So let's just take an example, very simple. Let's imagine that we have a variable x that follows the distribution pi1. And for the sake of the example, let's consider this to be the uniform distribution on the interval 0, 1. Let's consider another random variable y, distributed according to pi2, which we put as uniform in the interval 0, 2. So we might find many different joint distributions with those marginals. For example, we can consider x and y to be independent. Now, if you imagine what the samples xy would look like, we can draw the x-axis and the y-axis simply with a simple figure. We can draw a rectangle delimited by 1 on x-axis and 2 on the y-axis, and we can draw crosses uniformly in the rectangle. Now, another coupling of the same marginals is to say that y is equal to 2x, in which case y is still exactly distributed as a uniform in 0, 2, but you will see that on the xy plane, the samples are very different because now they're all on a segment, right? So those two distributions have the same marginals, but different joint behavior, which you can see in the scatter plot. And in fact, there are infinitely many couplings of those two distributions, and in general of two distributions. So those are just joint distributions. So what's the really big idea with couplings? The big idea is that if we have one distribution of interest, like pi1, and we want to understand it, so to understand a variable x that follows some pi of interest, we can introduce another variable y and relate it to the variable x in a special way. There are many ways of relating x and y, and certain ways of relating x and y and introducing the correct y will provide a lot of interesting information about x. And this idea dates back to the 1930s, the work of Dublin, for example, which we'll talk about in the chapter 3 of the lecture notes. So let's go back to the Monte Carlo methods and introduce our first Monte Carlo methods. First, we're going to look at methods based on transformations. So, a disclaimer, throughout the course, we will make this big assumption. We will assume that we have access to uniform draws in the interval 0, 1. That means we can ask the computer to generate draws or samples in the interval 0, 1. And this is not at all obvious. You have functions in all the software to do that, but it's not at all obvious what's going on to generate draws in the interval 0, 1, or in any interval. And this is a whole topic called pseudo-random number generation. So in this course, we will assume that we have access to a pseudo-random number generator, and we won't worry about it. So the question will be, how are we going to transform those draws into the distributions that we want, that will be potentially very complicated probability distributions on complicated space. So for example, if you have a uniform sample in 0, 1, you can multiply it by a scalar, you get another uniform in 0a now. If you add another scalar to it, you'll have another uniform distribution, this time in the interval b, a plus b. So we can modify a variable here using scaling and translation to obtain another distribution. More generally, if we have x following a distribution here denoted pi x, and if we generate y by applying a function g to x, then if g is a bijection, so it's a one-to-one mapping, then in fact we know what the variable y will follow. It's the change of variable formula. It will follow a distribution with density pi y that can be written in terms of pi x and in terms of the inverse transform g minus 1. So you'll see this Jacobian term appearing that multiplies the density with respect to x. So what it suggests is that if you have an x variable that you know how to sample to, and if you choose your function g adequately, then maybe you can create a sample y as a function g of x that can follow the distribution that you want, right? So perhaps by playing with the function g, you can reach your desired target distribution for your sample y. And this is a powerful idea which has in particular an application called inverse transform sampling. So that's what we're going to see next. Probably the most classical Monte Carlo method called inverse transform sampling. This dates back to the 1950s. So the assumption here is going to be that we're interested in a distribution in dimension 1. So defined on the real line or a subset of the real line. And we're going to assume the CDF is denoted by f. So f of t is a function that maps t to the integral between minus infinity and t of pi of dx. So it's the probability that the variable is less than the value t. So we can plot this cumulative distribution function. It's a function that takes value between 0 and 1. It can look like this, for example. We're going to introduce the inverse of the function, the inverse CDF, also called the quantile function because it gives you the quantile of the distribution. Let's denote it by f minus. So if we take a value u between 0 and 1, and you look up, thanks to the curve of the CDF, where the inverse is, that's f minus u. So it's the inverse of the CDF, but maybe the CDF might not exactly have an inverse if the distribution has a point mass. So in general, we define f minus u as the infimum among all x such that f of x is more than u. And so based on this inverse CDF, here's the algorithm, our first algorithm. We sample a uniform in the interval 0, 1, and then we compute x as the inverse CDF applied to the uniform. Then the resulting x will follow the target distribution pi of interest. So we can have a look at the proof quickly. The starting point is to write what's the probability that x is less than little t. So x is f minus of u. So we replace x by f minus of u. And then I invite you to do the calculations using the properties of the CDF to arrive at capital F of t, which proves that the variable x that we're talking about has CDF f, and thus it's the distribution of interest. I also invite you to take an example, such as the exponential distribution with parameter lambda. The CDF of this distribution is given by f of t is equal to 1 minus exponential of minus lambda t for all t positive. So you can pause the video and try to work out how to generate exponential draws based on the inversion of this cumulative distribution function. So now let's look at a visualization of the output of the inverse CDF transform method. So again, let's imagine a certain cumulative distribution function from R to 0, 1. What we do really is we sample a value in the interval 0, 1, say u1, we look up where the inverse of the CDF is, and that gives us x1. And we do that again, that gives us x2. We can do that again a number of times. And so when we do that, we realize that as we look at the pairs ux, of course, they all, by definition, they all lie on a curve, which is a given, which is precisely the curve of the CDF. And so this is, in fact, a coupling between the uniform distribution on 0, 1 and the target distribution pi. So it's in terms of the scatter plot, this is a scatter plot where all the dots lie on a curve. So we can add little crosses everywhere on the CDF. That's where our draws would be if we view them on the plane, on the subset of the plane with u and x. So, of course, the limitation of the method is first we need to be able to evaluate the inverse CDF, which might not be obvious. If your distribution is given in terms of the PDF, you have to do a little bit of work to get the inverse CDF. But more importantly, it's hard to generalize this reasoning in arbitrary dimensions because of the reliance on the CDF, which is hard to define in arbitrary dimensions. However, there are methods that still try to map simple variables like uniforms or normals to complicated distribution pi using ideas of transportation or so-called normalizing flows that have been in fact quite popular in the literature in machine learning in the past few years. And that can really be seen as a generalization of inverse CDF transform. So now we're going to move on to another type of method, a Monte Carlo method, that is applicable in arbitrary dimensions, but we'll see it has its own limitation. It's called rejection sampling. It's the other most basic Monte Carlo method. In particular, it's also from the 1950s, from the same original Monte Carlo pioneers. It requires PDF evaluations, this time, possibly unnormalized. So let's call the unnormalized PDF pi u. So it requires being able to evaluate this pointwise. And it also requires a proposal distribution, which we'll denote by q. And you can think of this as an approximation of your distribution pi of interest. So if you can, you have to come up with a distribution that is very close to the target distribution pi. But for this proposal distribution Q, you need to be able to not only evaluate the PDF, but also sample from it. There's a further assumption, which is that for all x, the ratio pi u of x over q of x is less than a constant m for some constant that you know, that you need to numerically know. Okay, so it's an upper bound on this ratio of density that you will need for the algorithm. And the algorithm goes as follows. You will sample a variable that is uniform in 0, 1, denoted by u. You will sample x from proposal distribution q. And then if u is less than the ratio pi u of x over q of x times m, then you output x as your sample from the target. Otherwise, you repeat. You sample a new uniform, a new x, and you check again. So there's a sort of a while loop in the algorithm. So the result of this algorithm, the resulting sample, the accepted sample, follows pi. We can consider the proof of this quickly. A good starting point is to consider the probability that x is in a set A and that u is less than pi u of x over q of x times m. This joint probability can be written as an integral with respect to the law of u and the law of x. In the integral, there's an indicator that x is in A, an indicator that u is less than this ratio, and the probability is taken with respect to the law of q and the law of the uniform, which is simply 1 in the interval 0, 1. And that you can simplify. You can do the calculation to get that it's equal to the integral of the indicator that x is in A times pi u of x divided by m dx. So then, from this expression, you can obtain the probability that x is in A given that u is less than this ratio. And that's the probability of the accepted sample, the one such that the u variable was less than the ratio. And doing the calculation as a ratio of probabilities, you get the desired pi of A, which means that x follows pi. So it's probably easy to see in an example or with a figure what this does. So let's look at a simple example in dimension 1, where the target distribution pi is a beta distribution with parameters 3 and 2. So the unnormalized density of this target distribution is given by pi u of x is x squared times 1 minus x on all x in 0, 1. As a proposal, we will take the uniform distribution on 0, 1. A very simple proposal. Note that it's not obvious a priori I had to sample from the target, so it might be a good idea to use rejection sampling. You might also try if you can figure out how to do it with inverse transform. Let's look at a figure. So on this figure, we can plot the unnormalized PDF pi u. It might look like something like this. And here the normalized proposal density, Q, which is equal to 1 on the interval 0, 1. And you can note that the ratio of densities is bounded by 1 here. So we can set the constant m to be equal to 1. It might not be a good choice, but we can do it because this ratio of density is always bounded by 1. And so then we draw x and u, and we see if u is less than the ratio of densities. So basically it means we see if u is under the curve pi u of x. So the first one gets rejected, but the second sample here gets accepted because the u value is less than the ratio pi u of x over q of x at x. And so the algorithm proceeds rejecting or accepting samples like that. So of course, you can also check that if your m is too large, the rejection rate is going to be high. Maybe 1 here, for example, is a poor choice of an upper bound for the unnormalized ratio. Let's look at another example in dimension 2 this time. So in dimension 2, again, it wouldn't be so obvious to do inverse CDF transform, but we can still do rejection sampling. So we're going to look at a simple example where we're going to plot -1 + 1 on both axes. We're going to look at the square of side length equal to 2 and centered at 0. And we're going to look at the circle, the unit circle. Define the target to be the uniform distribution on the circle. So pi u of x can be defined as the indicator that x1 square plus x2 square is less than 1. And as a proposal, we can use the uniform distribution on the encompassing square. So that's the indicator that x1 is in the interval -1, 1, and x2 is in the interval -1, 1 as well. This is not normalized, of course, because the normalization should be 4. So the algorithm is intuitive here. You basically draw from the square uniformly on the square, and you only keep the draws that end up being in the circle. And that, in fact, is exactly equivalent to rejection sampling, with a certain choice of the constant m, as you can work out if you're interested. So you will reject the points that end up in the corners, and you keep the points in the disk. You can do the same in any dimension with an encompassing hypercube, but you will see that the rejection rate would get higher quite quickly with the dimension. It's a good exercise to figure out what's the rejection rate of this rejection sampler. Let's move on now to another method. So we've seen inverse CDF and rejection sampler, and they both provide IID samples. This one is called importance sampling. It doesn't provide IID samples from the target. It dates back to, actually, I'm not quite sure, probably in the 1950s. There's not one paper that is attributed for starting this. We still have a target distribution pi and a proposal q, just like in rejection sampling. But this time, there's no need for an upper bound on the ratio pi u of x divided by q of x. So that's a relaxation of the assumption that we had for rejection sampling. The algorithm is simpler as well. We sample x1 to xn from the proposal distribution q, and we compute weights. Wi for the sample I is simply the ratio of the density of the target over the proposal, and we compute this weight for each of the sample. Then that's it, basically. The weighted samples that we obtain, which we can denote Wi xi, in a sense, they already approximate the target distribution pi. So there's no while loop anymore, no uniform draws. So what does it mean that those weighted samples approximate the target distribution pi? It means that if we compute the ratio of the sum of the weights times a function evaluation at xi divided by the sum of the weights, each weight is positive, this ratio converges in probability to the integral of h with respect to pi. And this is actually very easy to show. You can divide the numerator and denominator by little n and use the law of large number as long as some regularity assumptions are satisfied, which are being written. And so those are very simple. I mean, the first one just says that the absolute value of h should be integrable with respect to pi. And the second one, in fact, in this case, is always satisfied because the q density cancels out. So just then applying the continuous mapping theorem to two consistent estimators leads to the convergence in probability of this ratio on the left-hand side to the integral on the right-hand side. But note again, it doesn't provide any sample exactly from pi. So it doesn't provide really the same type of output than rejection sampling. On the other hand, you can see this procedure as being more efficient than rejection sampling because all the draws that you obtain from the proposal Q are utilized in the resulting weighted sum. There's no draws that are discarded. And so let's look at the same example that we had before and see what importance sampling would do. So we looked at an example where the target distribution was beta 3, 2, which has this density on 0, 1. The proposal was uniform. So what we would do is sample uniformly on 0, 1. We obtain those crosses. And then we compute some weights. And the weights are simply the ratio of the densities. Q here is 1. So we simply have as a weight the unnormalized density. So basically we attribute more weight to the samples that have a bigger density with respect to pi, which is very intuitive thing to do in order to correct for the difference between Q and pi. And in particular, we are not discarding anything, and thus all the draws that we've obtained from Q are being used. They're just given a different weights. Some draws might have a small weight, whereas other draws might have a bigger weight. In passing, we don't have to worry about any constants that we had in the rejection sampling algorithm. Here it does not matter because if you multiply the weight by a constant, that will disappear in the ratio that forms the approximation. And so any multiplicative constant has no effect on the approximation. So it can possibly work in high dimension, this method, but only if your proposal distribution is very close to the target distribution pi. And so it has to be really well chosen, and it's very hard to choose. So many people would think that importance sampling, in fact, doesn't work in high dimension. So for more precise statements about this, in fact, there's been some progress in the last few years. Paper by Agapiou et al. And a paper by Chatterjee and Diaconis, for example. Those references are in the lecture notes. They give a pretty good understanding of the performance of importance sampling as a function of a divergence, a certain notion of divergence between the target distribution P or pi and the target and the proposal distribution Q. So more precisely in terms of the chi-square divergence or the Kullback-Leibler divergence. And so in fact, some variants of importance sampling are still state-of-the-art and used a lot in statistics and machine learning these days. For example, annealed importance sampling, sequential Monte Carlo samplers are ways of automatically coming up with a good proposal for importance sampling. So we're reaching the end of the first video for this course. I will wrap up by looking at the relevant figures in the lecture notes, relevant to what we've just seen. So basic Monte Carlo methods such as inversion transform and rejection sampling. So let's have a look at the lecture notes. These are the lecture notes. So the first figure is meant to represent the fact that we might have different pieces of knowledge about the target distribution of interest. So what you see on this figure is on the top left, a probability density function of a distribution with 3 modes. On the top right, you see the cumulative distribution function corresponding to the same distribution. On the bottom left, you see the inverse of that cumulative distribution function. So this is the inverse CDF or quantile function. And on the bottom right, you see the histogram of samples generated from this distribution. So this is representing the fact that when we say we have a target distribution, we might in fact mean different things. We might have different access to different ways of characterizing the distribution. Let's look at the second figure. Figure 1.2 is a representation of the inverse transform sampling. So what you see is a scatter plot, in fact. So a bivariate plot with different points. And you see all the points are supported on a curve. If you look at the X marginal distribution shown on the top, you'll see that it follows, there's a histogram and there's a curve also. So what is meant to represent is that the generated samples follow the curve that we wanted them to follow, so the target distribution. And on the y-axis, you see the marginal is a uniform. And so those uniform draws have been mapped into the distribution that we want based on the inverse transform. Okay. This is also an illustration of a certain type of coupling between a uniform distribution and the target distribution. It's a peculiar coupling because the two components are related deterministically. In statistics, when you see bivariate distributions, most of the time, the components are not related deterministically. But here, by design, this is the case. Figure 1.3 shows an example of rejection sampling. So this is using as a proposal a uniform distribution on 0, 1, and as a target, a beta distribution. The PDF of the beta has been scaled so that its maximum is attained at 1, which is sort of a good choice in terms of the rejection rate of the sampler. And what you see is the points are drawn from the uniform distribution. And then another uniform is drawn, giving a y value to those points. And if the y value ends up, if the point ends up above the curve of the target distribution of the PDF of the targets, the points are rejected. If they end up below the curve, they are retained. So this is the principle of rejection sampling on a simple one-dimensional example, but this could work in more complicated settings. And the fourth figure is representing importance sampling. So what you see on top is a certain proposal distribution You can see a histogram of it and also a curve. So we sample, and the histogram of the samples would be an approximation of the curve. And what's seen in the middle is the log weights associated with those samples, where the weights are defined as the target PDF divided by the proposal PDF evaluated at those points. And you can see that here it's a good choice of proposals, because as the samples end up in the tails of the proposal, their weights end up being smaller and smaller. So the log weights being more and more negative means the weights are very small. This is a favorable situation for important sampling. It represents the fact that the tails of the proposal are heavier than the tails of the target. And so the weighted samples can be used to approximate the target, which has been done to produce this third panel. Okay, and that wraps up the first video for STAT 248. Next time, we'll move on in the chapter 1 of the lecture notes to cover Markov chains and Markov chain Monte Carlo.